Hey everyone, welcome to this Introduction to 3D Programming course. In this course, we're going to go over some basic introductions to the Rhino3D modeling interface, followed by an introduction to Grasshopper programming inside of Rhino, as well as an introduction to 3D programming inside of Python for Rhino. And then towards the end of the course, we're going to get into a bit of machine learning interfaces outside of Rhino, as well as some general coding interfaces like Google Colab Notebooks, which is a remote computing interface, making it easy to pass and share code, as well as run it from a browser. For this first video, we're going to be focusing primarily on an introduction to Rhino's interface, as well as some of its geometry types and modeling operations. In the second video, we'll get into an introduction to the Grasshopper interface for Rhino. So to begin, once you've installed Rhino, we're going to just go ahead and either click on the icon at the bottom of your desktop, or we can go to the Start menu and type Rhino, and whatever Rhino version you may have, just go ahead and click on that, and it should open up on your desktop. When Rhino opens up on your desktop, you should see by default 4 views like this. Each one of these views is a different viewing window or viewport inside of the Rhino interface. So right now we have toggled on perspective, and then additionally we have the top view, the front view, and the right view. This is so that in case you wanted to coordinate some kind of object dimensions between views, we can get this simultaneous view of the object, like whatever you're designing in top view. If you want it coordinated also in a frontal view, we can do that through these 2 viewports. Same with right view relative to the front view. So we can just check to ensure that our elevational or orthographic information, which is flat representations of the object, are all aligned. And at the same time, we can check the perspectival view of the object. So this is great for architectural drawings. It's also great for things like product design when you want multiple views to align, or you want to check aspects of each view. At the top, we have our toolbar. So we have just general tools located up there, and then just above it, we have the Rhino menus, which includes file, where we can save, import, or open files, and then you have edit to perform any file editing operations like selecting objects in the document, object visibility, or copy and pasting or undoing information. And then it gets into viewing options, and then we have curve, surface, sub-D, solid, mesh. These are all geometry types present inside of Rhino, which we'll get into in this video. After that, we just have some tools for things like Rhino script, Python script, transform operations, so this we'll get into as well, but operations that we can perform to edit the objects or geometry types that we instantiate inside of Rhino. Then we have really helpful tools like Analyze, which allows us to analyze our geometry for things like preparation for 3D printing, so that we can make sure that our objects are watertight. If we have some kind of secondary output, let's say we're doing some product design and we want to ensure that our object is watertight, then we can go to Analyze, Edge Tools, Show Edges, for instance, and it will show us which edges are not sealed properly or are improperly overlapping. That's just one instance, but it is a really helpful tool panel once you get more advanced into using Rhino. Then we have a render menu. So the render menu, depending on whether you're using an external renderer or not, like let's say V-Ray, which is actually kind of hosted inside of the Rhino environment, we can toggle options on for the internal Rhino renderer, or we can directly access things for V-Ray inside of here in addition to its own menu options in the toolbars panel. Then we have a panel menu, which is actually to toggle on different aspects of these toolbars or menus, so we can make edits for whatever our kind of display preference is. So generally when we're opening up Rhino, we start with these 4 views, but typically I just double click on the name of perspective, and this expands that one viewport so that the only viewport in our viewing canvas is the 3-dimensional perspectival space. So if I double click on that, left clicking, then we can enter into that kind of world, that 3D space, and then I can right click and drag to orbit. I can click shift and then right click and drag to pan. I can click control, right click and drag to zoom in and out. And then I can hit control alt, right click and drag, and this allows me to pivot. So this is a pretty crucial thing for architectural perspectives. So if you know that you're on the exact viewing point that you want, but you don't quite have that perspective angle set, this can be a really great tool for navigating around your scene. So control alt, right click and drag is a kind of pivot view. If you don't want this grid visible, then you can just type in this command prompt up at the top. So this is our primary interface with Rhino. It is a command-based interface, meaning on this command line, we can just type whatever the command is that we want. So in this case, we can type grid and then hit enter to send it to Rhino to run. It gives us additional options for that command. Choose grid property. So all I want to do is say show grid equals no. So we're changing that property show grid to a Boolean of no, or a false value rather than a true value. And that actually sends information to the display properties in Rhino to turn off the display of that grid. Now if we hit enter, we're done that operation. We can just see our axis in space, and we just are inside of that perspectival space. On the right side, your toolbars may look a little bit different than mine, so you may not have the named views here. I can just go ahead and drag this out or exit out of it to remove that from my toolbar so that it probably will now look a little bit closer to yours. So in this toolbar on the right, we have our properties, which are the properties of either the general viewport when nothing's selected, which we're seeing here, information about the viewport, the type of projection, so it is perspective. If we were in top view, it would say parallel, which is an orthographic projection, so no perspectival distortion. Then we have information about the camera placement. So when I was doing the pivot, if I do it here while we're looking at this, we can see that pivot makes the camera location not move, but the target information is what moves. So if you see that target information updating, whereas if I just right click and drag to orbit, then my actual camera location is moving, not the target, right? So orbit is orbiting around a focused target. If we had an object selected, the properties of that object would show up in this properties menu, in addition to some other things like our material that we might apply to that object, as well as some texture mapping or other properties that may come along with it. The next major tab here is the layers tab. So right now we just have one layer. This is going to be our primary scene outliner for Rhinoceros 3D modeling. So right now we just have default. If we wanted to add an additional layer, we can do that by clicking new layer, and I can say geometry samples and then click away, and that makes a new layer called geometry samples. We can edit the color or material of things on this layer by changing the information over here to the right. We can also toggle visibility or lock it if we no longer want to edit whatever is on this layer. The check mark and bold indicates whatever the current layer is. So if we were to make an object right now, it would by default be applied on the default layer. If we wanted it to by default be applied to the geometry samples layer, we would just need to double click on that layer. Now anything we make will be applied inside of that geometry samples layer. We can nest layers to keep our files nice and organized so that we can toggle or select relative to the layer structure and not just based on whatever objects we're placing in the scene. That's all I'm going to go through on this right side, and on the left side it's just important to note that we have a few default options for our standard toolbar kit, which are kind of quick selection options. So we have just a cancel option, we have point, line, curves, and then we have the circle, ellipse. So these are kind of 2D primitive objects, base geometric types. And then we have an arc, a rectangle, a polygon, fillet curves, which is an edit option to our curves, which are instantiated from one of these commands above. And then several other icons, which we'll get into on this left tab as we go through some of the geometry types. But one thing that's important to note is that you can either access things through the tabs at the top here. So I could click on Curve Tools and access Curve Tools there. I could click on Standard and access some general kind of document or viewing options in our Standard tab, or I could go to the Quick Select icons on the left and access whatever those icons may be. Alternatively, you can type the command in. So when you're just starting, it might be best to search for the icon so that you know what that option is. You may not know exactly what it's called, but as you get more comfortable with Rhino, you're going to want to just be typing into the command interface. It's much quicker, and there's also a kind of quick hint suggestion based on your most used commands, which you can also pre-program if that's something you're interested in doing. So to go ahead and get started, we're going to be going through a couple of the different geometry types available to you inside of Rhino. So the first one is going to be a point geometry. So right now we're in a three-dimensional space where this green axis here is our y-axis, as we see in this bottom left icon, which is our world axis icon. And then we have our x-axis, which is the red axis currently, and what we're not seeing is, let's call it a blue axis that's invisible right now, which is the z-axis. So that is our 3 dimensions in the three-dimensional space we're currently viewing. A point is defined by coordinates at the x, y, and z axes. So that is a 3D point, which is our primary point system inside of Rhino, as it is a 3-dimensional modeling program. So if I either click on this point icon here, or I type the word point and then hit enter, it's going to ask me for an additional prompt. It's going to say location of point object. I can now click into space, and it's going to project onto what is called the C-plane, which is the default plane or construction plane inside of Rhino. So if I click, that C-plane by default is the XY plane, so it will instantiate a point somewhere on the y-axis, somewhere on the x-axis, but we know it's actually going to be at the 0 point in the z coordinate plane. So if I click here, we have 1 point object added. If we go to properties and details, we can actually see the object description of that point. The point has been added, and it is precisely at 32.2751, comma, so that's the x coordinate there, comma 45.2025, and then as I mentioned, 0 on the z-axis. So if I go ahead and hit close and then delete that point, if I wanted to make that point at a more specific unit, then what we can do is go to grid snap. Now, in order to do this, it might be helpful to actually visualize that grid again. So we can just type grid in our command prompt, show grid, yes, enter. We now have that grid visible. And if I type point again, I can move this point around, but if you look closely, you can see that it's snapping to the grid units in space. So if I now click to deposit that point or construct that point geometry, select that point by left click and dragging across that object, and then go to details, we can see that it's now an integer value of 18, 10, 0. So those are the x, y, and z coordinates of this point. As I move this point up, let me just close this window first. So move this point up, it's still snapping, so we're snapping in the z-axis. If I hit ZS or type in zoom, it's going to give me additional options. I want to zoom selected, so zoom to the selected object. So I'm going to just type the S shortcut because that S is underlined, meaning the S is the shortcut to get to that command, and then hit enter. So I've now zoom selected, changed the camera target to this particular object. So we're looking at this object and framing it inside of our view. Now when I right click and drag to orbit, I'm orbiting around this object, centered on this object, and we can see the space moving around it in 3D. As I use my scroll wheel, I can scroll in and out from that object, getting closer or further away from it. And if I go to details, we do see that we're now at that 7 units up, because it's a positive integer, in the z-axis. So same in the y and x, and I can just hit close. These blue, green, and red arrows, as well as these blue, green, and red arcs, are what is called the gumball. So this gumball can be toggled on and off by the gumball option at the bottom of your Rhino interface. So that's off, and now when it highlights blue, it means it's on. We can do that with any of the options down here, which we'll get into later on. So if you just want to move by, let's say, an unknown dimension, then you can just click and drag this arrow. Right now our grid snap is on, so it's going to snap to particular dimensions, but we don't necessarily know how many units we've moved. And then I can move it down as well. If this was an object that could be rotated, which a point cannot because it's only defined by x, y, and z coordinates, then we could rotate it with these arcs. If we want to do a more specific operation, like move it x number of units, we could just click on the arrow, type a set number of units, and that will now move it 10 units in the x-axis. If we want to move it -10, we just type -10. If we want to move it -2, we type -2, and then we can do the same, and it's by default going to fill in our previous input. So that's -2. So we're now moving -2 in each axis. If we want to move it straight to the origin, let's say, then we can type a command to move this object or edit this object, transform this object. And this command is going to be called move. So I'm going to type move, hit enter. It's hard to see, but our point is now highlighted yellow without that gumball. But we can see that since my cursor will snap to the point, since my point down here at the bottom left is checked, this is called our O snap option. So this means our cursor is going to be able to snap to whatever geometry is selected there. So point geometry is selected. So I'll be able to click on this point, and then I can click anywhere in space where I want this point to move. If we want that to move to the origin, we can just type 0, 0, 0, or the shortcut for this is just 0. And then Rhino knows that 0 is a shortcut or a kind of nickname for referring to the global origin. The origin being the 0, 0, 0 point of this 3D space. So if we hit enter, we see that point now show up at the origin, so the kind of intersection between these red, green, and blue axes. If we look at the properties for this, we now see that that point is at 0, 0, 0. So the next geometry type is actually going to be derived from a point, and this is going to be a line. So a line is just simply defined by 2 points in space and the connection between them. So if I were to drag this point out, and then drag it out again in the other 2 axes, and then type line, what it's going to ask for is the start of the line, which I can click in space on that point, and the end of the line, which I can click on that second point. So that connection between 2 points in space is going to make a line. I could delete those points as well and simply just type the command line, and now I can left click anywhere in space and then right click anywhere else in space, and that's going to produce that line. I can then select the control points or endpoints of that line and use the gumball or the move command to move it wherever I might want in space. So we now have that line in our three-dimensional space. Similar to a line, you may have heard of this in a math class potentially, but there is something called a vector. A vector is incredibly important in computational design, and the basic principle is that it is a kind of ray or partial line, which is defined as 3 coordinates, but those 3 coordinates, almost like a line, are the x, y, and z components of that vector. So a vector has x, y, and z components, and if it's set at a given length, then that is almost equivalent to the definition of a line. It too can be defined by 2 points and the connection between them. So that's one way of defining either a line or a vector. And you can actually solve for any vector output as the endpoint subtracted by the starting point. So anytime you're using some computational reference to a point or a vector, they're going to look pretty similar as x, y, and z coordinates. We don't actually have an option for that inside of the Rhino interface, as a vector is a less often visualized thing, since it's just a ray from a starting point into space. The closest thing we have to visualizing a vector in the Rhino interface is actually going to be a point. This may be a little bit too complex for this video, but I'll mention it just in case anyone's interested. If you actually type point and then draw a point in space, so I've moved that, or let's type point, and then I'm going to type the coordinates here, so 1, 12, 4. That makes our point at 1, 12, 4. So the vector that is actually defined by 1, 12, 4 can be thought of as a vector drawn from the origin to this point. So a 1, 12, 4 vector, again, without a defined starting point, can just be understood as from the origin to the point location. Again, being constructed with the kind of concept of 2 points, one being the origin point, the second being the point we just drew. If you're not fully understanding that, that's totally fine. We'll get back to it later on, but that's going to be a critical component of our Python coding, especially when we get to things like agent motion. So again, we can draw a line in space. A line is defined by just 2 points. If I draw another line and connect these two, we now have 2 lines. When these are joined together, so I can type join to edit both of these lines and join them, we've now constructed a polyline, which is composed of 2 line segments defined by 3 total points, each of which is a control point on the polyline. So now if I click on this point and I drag it, we're actually editing both line segments, and they stay connected as a polyline is just a combination of line segments. I can select these 2 lines or polyline. I can click Alt to copy. I can use the red arrow here to copy them in that one particular axis, or I can delete that, select the original line and type copy. I can click on one of these points, and then I can click on an additional point, and it deposits that copy of our object. If we wanted to rotate, we could rotate just using this gumball here by clicking on one of these arcs, or we could type rotate in the command line, hit enter. It's asking for the center of rotation, which we're going to use as this endpoint and the start of our second polyline. And I'm going to then click for the first reference point. That's going to be a point on the polyline. So I'm going to click to reference that point. And now by default, we're snapping to orthographic rotations. So I'll just snap all the way down to -90 degrees not the angle of rotation, -90 degrees, but we're snapping so that the line is oriented relative to the y-axis. So we now have those two polylines, still separate geometry. If we select them again and type join, we now have one polyline. If we go into details, we can see that this is defined as a polyline with 5 points now, and it gives us each of those points. So it's important to note that a polyline is defined by the connections between control points, similar to a line, which is defined by 2 points. But this just has multiple what are called control points or vertices of the polyline that define it. From a polyline, we could rebuild this or re-understand this as a curve geometry, which there are many ways of drawing curve geometries inside of Rhino. One of those is called a NURBs curve or a control point curve. So if we click on this icon on the left, which is just below the polyline or line segment command. So another way of drawing this polyline is by typing polyline in our command and then clicking to deposit the points in space. Additionally, we could click on the icon on the left called Polyline, and we can click to deposit those points in space. And whenever you're done, you just hit enter or right click to be done that polyline. Now, if we're drawing curves, it's very similar. We can click on this control point curve icon. So I can just go ahead and left click on that. And I'm gonna just draw points exactly on the point locations of the vertices or control points of these polylines. Additionally, I could just type curve, and now I can do the exact same thing by depositing a curve at those control points. So we can see if we left click that we actually have two curves there exactly in the same position because we used the exact same command in the exact same points to create two identical objects. How these NURBs are actually defined is a kind of calculus definition for the division connections between segments on this polyline. It starts to get a little bit more complex, but I always like to show this to give an understanding of what this NURBs curve actually is and why it didn't appear in kind of base geometry principles until relatively recently when basically calculus was invented. Up until this point, just polylines and arcs were used, as well as different combinations of arcs, making ellipses. So the basic idea here is that to construct a NURBs curve, we actually need to first explode the polyline. So now we have each of the line segments, and then whatever the degree curve this is, which by default it's degree 3, is the number of divisions or a number of iterations of division connections that we are going to need. So if you know anything about differentials in calculus, it's measuring the rate of change, or it's measuring the kind of tangent at a particular given point along a curve. So instead, what this is doing is it's actually constructing a curve solely defined by the division connections from one polyline segment to the next polyline segment. So those construct the tangents for this resultant curve. And I'll explain this visually just to give an idea of how these are actually defined. So we can start by actually deleting this NURBs curve, typing curve again. I'm going to start by changing the degree to 2, and then I'm going to deposit a control point for this curve. We'll start by just doing it at those two segments of this polyline. Now, if I explode this polyline, we now have each line segment divided into its own object. And now on each one of these line segments, I can type divide, and I'm just going to say divide into 4 equal segments. So 1, 2, 3, 4. We've divided this line into 4 different segments with 3 division points on it. I can do the same thing for this second line segment. And now the idea is that we're drawing connections from the 0th or first point, which in coding is defined by 0. So the 0th point to the 0th point on the second line. And then we're starting from the first point, or second, but the 1th, if you want to think about it like that. So the index 1 point to the index 1 point on the next line, and then index 2 to index 2, index 3 to index 3, and index 4 to index 4, which is just that full line segment. So now each one of these is actually defining a particular tangent point, which we can get by taking this NURBS curve and selecting all those tangents and typing intersect. So besides the ones where our tangents are intersecting, which we can just go ahead and delete, we can see that there are 3 points of intersection exactly at the location where these lines are tangent. So if you do that not with 4 divisions, but with divisions approaching infinity, this is going to define our NURBS curve. And this is why we couldn't actually do this until calculus was invented, because we had no way of approximating infinity or driving things to infinity. An interesting fact is this is actually why in most 3D modeling programs, something that we're going to get into later, which is called a mesh, is much more computationally light than something that is called a polysurface, which is a version of these kind of infinitesimal or mathematically defined surfaces. This is because we have to define it using that infinitesimal kind of approaching limit to define the surface. But a mesh is actually defined discretely, meaning whatever you're seeing in the mesh is the actual information in the mesh, no more. So this is incredibly easy to compute. Or let's think about it like a polyline. A polyline is only defined by those vertex points, whereas a NURBS curve is defined by all of this math going into it. So a NURBS curve is much more computationally intense, just like a polysurface is much more computationally intense. And we'll get into what a polysurface exactly is in a moment. So if we were to do a degree 3 curve, we'd actually have to now increase the number of segments. So we'll have to use 3 segments this time. So if I type curve, go to degree 3, I can left click, left click, left click, and left click. This is because we need at least as many control points as the number of degrees plus 1. So we need 4 control points to make a degree 3 approximation. So if we wanted to mathematically define a NURBS curve that is of degree 3, we can start similarly to the previous one, defining a degree 2 by dividing each one of the segments into, this time, 4 additional segments. Now I'm going to draw those connections from the second point to the second point, the third point to the third point, and the fourth point to the fourth point, and then do that from the second segment to the third segment. So I'm just drawing lines across here. Now you can see that's quite a bit off from the desired output line. To make this a little bit easier to see, what I'm going to go ahead and do is take this curve, and we can just change the display color to green. And I'm going to take this polyline, and we're going to make this first degree, we're going to make this blue. So we'll have the first degree as blue, and now the second degree, which is quite a bit off, right? So it looks as though it's wrong. We're going to go ahead and change this color as well. We can change it to cyan. What degree 3 indicates is actually that it's not this first degree, which is the polyline. It's not the second degree, which is defined by the first round of these tangent lines drawn from the polyline segments, it's actually that third degree, which means divisions from these tangents. So divisions on these tangents drawn as tangents to this degree 3 NURBs. So it might make more sense when we actually do it. So we'll go through another round of dividing each one of these curves. So divide, 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 divide. And we're going to do the same thing on these 2 to 3 connections. So we now have each one of those divided. So now when we draw this additional line, which is the third degree, which should be tangent to our green NURBS curve here, what we're going to do is take the index relative to which index curve it is. So here we have the first division curve. We can take that first division point. So it's not the 0th, so it's not the 0th point, but it is the first, so it's the first point. We're not going to connect that here to the first point on the second curve, but we're actually going to connect it to the first curve here on that second set of divisions, right? So we have now a group of 3 and a group of 3. We're taking the first of the one group of 3, connecting it to the first of the second group of 3. And we're connecting both first points. So I'm going to click to make that, and we can see that that is tangent. Now on the second curve here, we don't want the first point, we want the second point, which is right here. So we're going to take that second point, connect it to the second curve on the second group, and its second point, which is right here. Now we're going to go to the third curve. So that's this third curve here. We're going to go to that third point. We're going to find the third curve in the second group, and we're going to go to its third point. And now we have these 3 tangents, which we can change the color of to be maybe orange, so that it's a little bit more obvious. So those orange lines there are defining that degree 3 curve, which is defined by this same operation, but just drawn out infinitesimally so approaching infinity, which is requiring calculus to do so, but that is the mathematical definition of these curves. So behind each one of these operations to construct the geometry inside of Rhino, or any 3D modeling program for that matter, is some similar mathematical operation, except, as I mentioned, with discrete geometry types like something like a mesh, which we'll get into momentarily. Now, similar to this definition of a curve or a Bezier curve of any degree from the definition of a polyline, if we wanted to construct a series of these curves, like let's say we take this curve here, I'm going to copy this over to the side so that we can see it a little bit better. I'm going to zoom selected by typing ZS, enter. We now have this curve. Now, if I wanted to copy this curve up, so I'm going to use this blue arrow and hit Alt, copy it up once, twice, 3 times, 4 times. What we're starting to do is define a surface or a kind of plane drawn across these curves here that can make a surface in 3-dimensional space. So what Rhino defines as a surface is actually just going to be an infinitesimal calculation, a mathematical calculation of stacked or connected or interpolated curves, right? So as the divisions here goes to 0, we're going to get the definition of a surface. So another way of doing this is to copy just one curve up. And if we just wanted that vertical extrusion or vertical surface, we can type Extrude Curve. So this is a surface. If we switch our view to shaded view, right now we have our settings set to wireframe. This is just going to display the actual edges of any geometry or just wires or curves. So if we switch to shaded view, it'll actually shade that surface approximation, which is defined by the curve profile we had on both ends of the surface and straight lines drawn between them. So it is a singly curved surface, meaning it only has 1 degree of curvature or 1 axis of curvature, which is the axis that that profile was drawn in. The top is flat, the bottom is flat relative to the curve. So we know that our curve was drawn flat, and that's why both top and bottom profiles are flat. So what's actually happening here is we're taking some line on each point of this curve, and we can snap this line to vertical, and I'm going to click on this endpoint, draw up, click, and if we were to just copy this line as many times as we possibly could onto points along this curve, and then let's say copy this profile up just to make it abundantly obvious, we would basically get the definition of that extrusion. If we wanted to do this with 2 different curves but still connect them, so I'm going to just copy this one up, make an adjustment to it, this would be done with a lofted operation. So a loft is going to be defined by the connections drawn similarly between divisions on one curve. So if we just divide and divide again, and then draw the connections between these, very similar to the Bezier curve definition from a polyline. So this is a kind of infinitesimally small calculation of the connections between 2 curves. So as those divisions go to infinity, meaning we used 4, if we use 7, it's slightly better. If we use 10, it's even better. If we use 10,000, it's even better. But if we use infinity, then it's the actual definition of the surface. So in order to get that, we can just type loft, and it's going to ask us for the curves to loft. We can select one curve and then the next one, hit enter, and then hit OK. And it's now going to define that lofted surface with infinitesimal resolution, meaning it's a kind of solid, opaque surface inside of Rhino, which is really just a very tight bundling of those curve definitions drawn out as connections between those 2 curves. If we didn't want to connect with a line, let's say, but instead we wanted to draw some curve here or have some profiled edge, we could type rebuild and rebuild this 1 line segment as a degree 3 curve. So let's say we wanted the curve profile on top connected to the curve profile on the bottom here, but we wanted something like this as a kind of curvilinear set of profiles sweeping along them. Well, we can use the option for sweep, or the command for sweep, which allows us to take any 2 rail curves like we have at the top and bottom. I'm going to just go ahead and delete these division points that we've drawn out. So 2 rail curves. And this is going to be indicated by sweep 2, where sweep 1 is just defined by 1 singular rail curve. So if we type sweep 2, it's going to ask us to select the first rail, which is our bottom rail, select the second rail, which is our top rail, and then our sweep shapes, which are the profiles that we want to sweep. So if we did this with a straight line, then it would just be the same thing as lofting. But if we do this with a curved profile, now we're going to get a doubly curved geometry, meaning curved on 2 axes. And we get this kind of profile swept all the way across that geometry. If we wanted that profile to change as it goes across those 2 rails, we can draw another line here at the end, rebuild this, select the control points, again type sweep 2, select the rail at the top, the rail at the bottom, and now it's going to prompt us for our sweep shapes. We want the profile at the beginning and the profile at the end. It is going to perform the interpolation infinitesimally or mathematically so between these 2 profiles. So if we hit enter, OK, we now get this kind of bellowing out on the start, and then it slowly transitions right about here to this concave inward profile at the end. So you get that smooth transition between not just the two rails, but also the two profiles. Another way to define a surface like this, if you have 4 curves defining a surface that, a compound surface like that, is going to be called edge surface. So you can type in edge, SRF, which is to indicate an edge surface. It's a kind of nickname for surface. And we're going to get pretty much the exact same result because it's just a different way to connect those surface conditions. If we type in edge surface and we wanted to add thickness to this surface, we could type offset surface. It gives us an option to flip the direction and distance. So I'm going to type for the distance by clicking distance or typing D for distance and then typing 30. We have options for sharp corners, which I'll keep as yes, solid as yes, and then we'll keep the direction inward. So I'll just hit enter. Looks like 30 is way too much. So I'm going to change that distance to 3 and hit enter again. We can see that when it performs this operation, since we're projecting these edges inward, it is giving a kind of kink here because it's not able to successfully solve for that. So one way is to either offset it with a shorter distance, so less thickness, which it is working quite well, or offset it outward so that it doesn't get that kinking as the surface tries to project inside itself. If we were to do that same offset outward, but we select solid no, we now have a gap between these two surfaces. If we had this and we wanted to connect it, so let's say we happen to have these two surfaces, we want them to be solid to 3D print, one operation we can do is type dupe border, which gives us the duplicated open border of both surfaces. We can just select and make sure we've selected both duplicated borders, so those are joined curves, and then we can type loft. And this is going to be pretty much the same operation as offsetting solid. It's just doing that in 2 steps instead of 1. We now have 1, 2, 3 surfaces defined here. And if we want to join these as a solid, we need to select all 3 of those, type join, and now it's going to construct what is called a polysurface, which is a joining of multiple surfaces. And if you were to 3D print this, you would want to see that in the properties menu, it says closed solid polysurface, right? So if we go to details, we should also see here closed solid polysurface with 6 surfaces. It's saying 6, not 3, because actually those edges that we lofted are defined by 1 surface on the top, 2 on the sides, and 1 on the bottom. So 4 plus the 2 that we had from the offset open surface, that makes 6. So that's the kind of construct of that solid poly surface. Now, an additional way of creating a poly surface or solid NURBs geometry defined mathematically is going to be a primitive. One of those primitives is going to be a sphere, which we can just type sphere. It's going to ask us for the center of our sphere. We can click to place that center, and then it's asking us for our radius, or we can just click a second point in space to define that sphere radius. So I'm going to just type 10, enter, and it gives us a sphere with radius 10, so diameter 20. We can do the same thing with box. Draw a box, it's asking for width and then height. So we can define that by a rectangle at the base, 2 points at the base, and then click again for the height definition, or we could have typed in numbers to define that. We can also do things like cone, click to set the base, 10 for a radius of our cone, 20 for the endpoint. We can also do a T-cone or truncated cone, which is defined similarly, but this allows us to actually give a radius on the top as well. And then lastly, we can do a pyramid as well. And we can define our pyramid by any number of sides, but we'll just stick with a 4-sided pyramid here. So these are what are called platonics or primitives, which are mathematically defined kind of base geometry types, versus the NURBs geometry here, which is defined by these kind of mathematically swept or infinitesimally calculated set of surfaces, which are really just line or curve connections between lines or curves. Lastly, similar to these solid geometries is going to be a mesh. So as I mentioned, since these what are called polysurfaces or NURBs geometries are defined mathematically, they're often much heavier computationally, meaning they can slow down your computer. A mesh, on the other hand, is going to be defined by a discrete number of, let's say, vertices. So a mesh is defined by points in space and the connections of those points, which is very similar to our polyline. So you can think of a mesh as a polyline type of geometry, and these polysurfaces are more like this NURBs or Bezier type of geometry that are calculated mathematically. So if I were to draw a bunch of points in space, and then draw line connections between each of these, and then group these, so each one of these areas that I've now enclosed would be called a face, where each of these lines would be called an edge, and each of these points would be called a vertex. So that is a mesh geometry, and it's only defined by this information. It's not defined by any additional information. So the edges are just the topological connections or the kind of bridges between points in a network of points, also known as vertices. So we can start by just redrawing each of these primitives, but as a mesh. So we'll actually start with a mesh plane. And it's going to ask us here to draw the first corner of this mesh plane. But then it's also going to ask us here the X count and Y count. This is part of that discrete parameter, meaning there's only so many units or only so many vertices in the X-axis and Y-axis. So if we leave those both at 10, when we click those 2 points to define that mesh, we see it's an open mesh, meaning it's flat, has a front and back face, but no thickness, and it has 10 units in each axis. So 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 faces in both axes. If we were to draw another one, so type again, mesh plane, and change that X count to 1 and Y count to 2, let's say, and then draw another plane, we now just have one face in the X-axis and 2 faces in the Y-axis, 1 in the Y and only 1 in the X. If we wanted to separate these, we could type extract mesh faces, select a face, enter, and we now have the mesh exploded into 2 separate meshes based on their faces. We can do the same thing for our original one. So extract mesh faces, select the faces we want to pull off, and then we can pull those off. So these are separable types of geometry, but are only defined by whatever exists in their definition, meaning they are discrete. They're only defined by the 10 by 10 units we originally used. And now we've split those off to make one mesh that is a 2 by 2 mesh, and the other which is roughly 10 by 10, missing 4 kind of corner faces. Additionally, we can make a mesh sphere. So these are constructed by just typing the word mesh and then whatever the primitive name is. So mesh sphere, mesh box. We can also set the resolution here. So that was a resolution of 1. We can set the resolution to be whatever we want it to be in each axis. And we now get a mesh with those individual resolution settings. Okay. So to further illustrate the difference between these two geometric types, if I go into, let's say, the sphere, select control points, so that's this icon here to the left, show object control points. So I'm turning the control points, which is like this hidden polyline for the mathematical calculation of this sphere object. And I now select one of these points and drag them. So select, drag in space. I'm actually editing the surface of this sphere, or the kind of cage or polyline that defines that sphere, but it's still smoothing it with that kind of infinitesimal calculation of what that sphere is. So it's not literally where these points are, but instead it's the approximation of the surface relative to these points. That would be the same for any of these NURBs or polysurface geometries. If instead I do that with this mesh sphere, turn the points on, every single vertex that's present on this mesh sphere is its own discrete geometry. So it is defined by that literal vertex, not a cage controlling some mathematical calculation. So if I move this vertex, it is literally just that vertex, meaning I have a sharp deviation now right where I've moved that vertex. If I grab a bunch of them, we can pull them all out, but it's no longer going to be the smooth sphere approximation. And same thing with these mesh boxes. If I select one of these vertexes and pull it out, we have just that one vertex moving, and actually this face is now composed of two triangles with a connection between these points, which causes a kind of folded face. You can almost see that there. And if I select the mesh and type triangulate mesh, we can actually get that drawn out for us, where there was an invisible connection between those two mesh points on the face. Just like with the NURBS geometries or the poly surfaces here, where we started with a single surface, zero thickness surface, and then we joined it or offset it to be a thick version of it, we can do the same thing with a mesh by typing offset mesh. And then we can set the offset distance, which I believe we use 3 for the poly surface, so we can use 3 for this offset as well. We can decide whether we want it to be solid or not. So I'm going to say solid, yes, hit enter, and we now have a thick offset mesh, which is a closed mesh, meaning it is watertight and could be 3D printed. We could do the same thing with any of these geometric types. We could also go into any of these NURBS geometries. So I'm just zooming into one of these. We could type explode to explode them. I could now select just this outer portion of the cone, so not the two top caps. Could move this over to the side to just prove it is a single surface with no thickness, and then type offset surface and offset this. When I just offset that, we offset it with no solid Boolean selected. So if we just click on solid or type S and then yes, we can change that solid option to yes, and we can make a closed solid poly surface that is just the thickness of that cone. You'll notice that when we offset a surface, it happens tangent to that surface, meaning we have a slight lip here. If we actually wanted to control that offset so that we just offset this curve exactly flat and offset the top curve exactly flat, what we could do is type dupe edge, select this bottom edge, type offset, type 1 to give the distance for the offset, type dupe edge again to to duplicate the top edge, type offset, no offset surface, just offset, and we're going to offset that the same thickness. We can now loft between the bottom edge and the outer edge. We can also loft between the two top edges. And then we can loft between the two offset edges. So this is giving us that closed volume. So we now have 4 surfaces, an inner surface here, 2 top and bottom caps, and then an outer surface, which if we type join, we can join to become one closed solid polysurface. Not only is this great for understanding 3D printing, where we need closed solid polysurfaces to be able to slice and 3D print, but it's also great for what are called Boolean operations, where we can actually add onto or cut into or intersect solid objects inside of Rhino, whether they're meshes or polysurfaces, in order to create some kind of adapted version of it. So let's say I had this thickened cone, this kind of cone surface, and I actually wanted to subtract out this pyramid from it. I could bring this pyramid over here, so I'm just moving it with the gumball in space. And I could use one of the Boolean operations. So I'm going to just type Boolean, and we see that we have options for Boolean to objects, Boolean difference, Boolean intersection, Boolean split, and Boolean union. So if I use Boolean union, it's going to add one to the other, and all space that is contained within it is now going to be contained within this joined object. So you can see here, they've actually been intersected and joined together, connected or combined together. So this is an additive operation. If I again type Boolean and now type difference and select the one that we want to subtract from, so that's going to be our larger cone, and then hit enter, and now select the one we want to subtract with, our pyramid, and hit enter. If we now delete this pyramid object, we can see that we've carved that pyramid kind of doorway or opening into our solid polysurface cone. It's still a closed solid polysurface because Boolean operations are going to do solid carving and preserve the solid quality of whatever object they are carving into. They are called Boolean operations because they are either yes or no. So they are calculating either whether something is inside or outside of something. So a Boolean intersection is going to only calculate the kind of Venn diagram of where both objects have an inside portion. Meaning if I select both of these and type Boolean intersection and say delete input yes and hit enter, it's only preserving where both objects have an overlap of where they have an inside portion. When we do the same with Boolean difference, what it's doing is saying delete wherever it's inside of the pyramid from wherever it's inside of the cone. And for Boolean union, it's saying actually to just combine wherever it's inside for all of them and make a new object that contains all of that inside of its object. So let's say we wanted to add these together again, so Boolean union. We now have that kind of remnant from both of these being added together, so we see both surfaces still, but it's actually in an even plane. So if we want to clean that up, because Boolean operations, since they're doing these kind of combinations, quickly make your file messy or your geometry messy. What we want to do is merge those surfaces to make them a flat plane again, combine them into one clean plane. So we can do this by typing merge all coplanar faces. And it actually looks like it struggled with that in this particular instance. So if it isn't able to do it, we can actually just do it manually by typing extract surface, click the surface you want to extract. It's now exploded from the rest of the surfaces. Select your object, which is now an open poly surface, and we can just type cap, enter, and it's now going to cap that flat bottom. What we're seeing here as those divisions are just the remnant curves, which we can either delete or we can type hide to put out of our view in Rhino. If we want to show those curves again, we can type show. So we now have that solid unified bottom, and we have our portions of our pyramid and our solid cone. To start to smooth the transitions between these two objects, which have kind of harshly combined together, we can type fillet edge, and this is going to create a radius fillet on the edge wherever we select. So we can start with the pyramid edges, and we can use a radius of 0.5, so half the thickness of this cone. And I'm going to just select these outer two radii and hit enter. Sometimes it has an issue with sharp points like this, and it's going to create an opening. We could try just doing one edge at first, and it seems to have done a slightly better job with just one edge. We could also try one of these inner radii and see if this can smoothly transition from the pyramid to that conic geometry. Now we could try this other edge again and see if it can do it. Sometimes it will give you an error like this, where it's actually just produced this kind of radius geometry for you to try to manually split. So if that is the case, you'll have to go through and take your base geometry, and using the split operations, type split, select that radius and hit enter. It's now cut off a portion of our geometry, which we can delete. We now need to select that kind of radius piece that we just cut our geometry with, hit enter. It's asking for the cutting objects. This time we're going to cut the radius object with our base geometry. Now we can select the part we don't need, and now we just need to join these back together. When we're done, we always want to clean it up with a merge all coplanar faces. We want to just check and make sure that these are cleanly joined together. We could do a similar operation to fillet with a command called chamfer edge. So this is just, instead of rounding, it's going to create a kind of beveled edge. We can use a 0.25 radius or edge distance to chamfer the inner edge here. We could also chamfer each of these inner edge connections so that there are no sharp edge connections between that pyramid and our cone. So this will make a stronger connection if we were to go in to 3D print those. If we wanted those inner edge connections to be slightly larger, we could set this to 1. Again, select each of those edges. And now we have those edges chamfered. Lastly, to save your file inside of Rhino, there are several ways that you can do it. You can just save the entire file as a whole by going to File, Save As. Additionally, you could select an object, type Export, or go to File, Export, and you would be able to export as the Rhino native file, which is a 3DM file. Okay, that's all for the intro to Rhino's interface. We'll get into one quick exercise that goes through some of these topics, but takes you from start to finish through a couple of these different steps in a much more concise way to challenge some of these skills that we've just built up in this first video. And then in videos to follow, we're going to get into Grasshopper 3D programming as well as Python 3D programming.